In the next subsection, after introducing the notation for string matching, I want to look at the very first and simplest string matching algorithm, and that's just the brute force method. Normally, brute force sounds really slow, but in this case, you will see brute force is not as bad as it may sound. A general thing that is true for almost all of our algorithms for string matching is that they can be described in terms of guesses and checks. And here, a guess is a position in the pattern, in the text, at which the pattern might start. So it's a guess because we don't know yet, but whenever you have a text, T, a long text, you can always try and guess that the pattern might be found at this position, starting at this position. That guess may or may not be justified, and initially, if you know nothing about the text, any guess might be justified. But as you learn more about the text through comparisons, some guesses are becoming impossible. The way to find out is a check, and a single check is a single comparison of two characters. We sometimes write this as this shorthand. So if you start at position I and you check the jth character in the pattern, then this is really doing this comparison. There's one character here, and you compare if that one matches the corresponding position in the text. That's all that is written here with the appropriate computation on the indices. Okay. So algorithms will differ in what guesses they make and in what order and what type of checks they do. And that's the process. But these two things will reappear in the algorithms. Some simple observations are that if you want to verify a correct guess, so an actual occurrence of the pattern, there's no way around doing M checks. Remember, M is the length of the pattern. That was something in the notation, but I didn't stress it today, so maybe just to recap. You need M checks to verify that the pattern is really found at a certain position. So there's no way to really save on that. But if you want to debunk a guess, if you have a guess that is not correct, then it might take much fewer checks to recognize that this is incorrect. A single mismatch is actually enough. So it will be interesting to see how we can get the mismatches, the incorrect guesses, sorted out quickly. Whereas for the correct guesses, there's not so much you can really do. The cost measure that we will mostly focus in this unit is the number of character comparisons. So that's individual characters from the alphabet, one in the text, one in the pattern, or maybe also between text and between pattern. And we compare whether those are equal or not. The only thing we can do is really check Ti equals Pj. That is what we can do. I'm stressing this because, for example, we cannot ask if one character is smaller than the other lexicographically or something like this. We will not need that in the algorithms in this section. An obvious bound on the cost that we can always get by with, unless we're doing redundant comparisons, is n times m. There are at most n guesses, actually n minus m are enough, but that's roughly n. And to check whether each guess is correct, the worst number we can need is m. So that's really an upper bound on the string matching problem. And if m is very, very small, if you're just looking for a pattern of 2 or 3 or 5 characters, maybe m times n is really not that bad. It's essentially scanning the text once. Now let's look at our first algorithm for string matching, and it's a very simple one. It's brute force, so it says try all guesses and do the checks just as they come. The only slight optimization that's built into this is that we stop if we have a mismatch. We don't stupidly keep going if we already know that the current guess must be incorrect. That's the only thing. So in code, that means we iterate through all the guesses. These are exactly the guesses that you've seen on the previous slide. Then we iterate j from 0 up to m-1. That's all the positions in the pattern, left to right. And if we ever find a mismatch, that means we stop this inner loop. If we keep running the inner loop till the end, that means if j is m after the loop, then we found a match and we return that position. Remember, we just returned the first match, so all we have to do is return this position I at this point. Let's do an example just to make this clear. Let's see. Well, maybe black is best to read. So what these colored boxes symbolizes, so here's the text, right? And we try to fit the pattern in here. And the pattern here is ABBA. So we do the comparison with A, and that actually matches. The second character B matches too. The third character matches as well, but then the last one is a mismatch. But we had to look at all the characters here. Now, okay, that was not a match. Maybe we try the next guess. So we start with B, but that's immediately a mismatch. The pattern starts with A, so we don't have to compare all the other ones in this position. Same thing happens here and here. Then again, A is a match, B is a match, but here we have a mismatch. So we don't have to compare this one. And this goes on. Here we have a match, a match, a match. And then actually here we find the pattern. So, well, had I remembered what number was the guess here, so that's 0, 1, 2, 3, 4, 5, 6. So we would return a match at position 6 at this point. That's all that happens. Here's that written in nicer font. And if you count, then you see you need 15 character comparisons in this example. Whereas this product, the upper bound n times m, is 44. So that's, I don't know, a third of the cost. That's not that bad. But it was a small and specific example. What's interesting is that this algorithm, essentially in the way I wrote it there, even though hidden deep in a hidden function, a private function, the Java library has a method called string index of. And this one is essentially implementing this brute force method. So it can't actually be such a bad method, right? Now, this is also my take on the brute force method. It often is actually good enough. But sometimes often is not good enough. We'll see. And for natural language text, where we have specific words and not all possible combinations of characters really occur, only the specific small subset of our dictionaries really occur. So it works fairly well for natural language text because of that. And for completely random strings, it also works well because you often get early on mismatches if everything's completely random. But it does become pretty bad in examples like this. If the text is all A, so the pattern is all A's except for a B at the end, you always keep comparing from the beginning. You already know there's this B at the end, but you keep. And what's worse, you know that there's all A's up here, but you forget this. You don't use that knowledge for the next guess. And so in this case, you do get essentially the worst case bound of n times m for the brute force method. So if there's a chance that this is what happens in your application, the brute force method is not good enough. And if you need strong guarantees about what can possibly go wrong, because maybe the user supplies the text and pattern that you're searching, then the brute force method just doesn't cut it. One observation that leads into the next section is this is a particularly bad input which has a lot of self-similarity. What makes this redundant here is we already knew there are A's in the text, so why check the same A's again here? And this kind of redundancy or superfluous comparisons should be able to be avoided, and that's something we'll look into. And yeah, so we should be able to exploit these redundancies both in the text and in the pattern. And that's what we'll look at next. If you have any questions, then please let me know at this point. It's always a good time. Okay. Then let's move on. I have a little roadmap here because basically this week and the unit 6 that we'll talk about in a week or two, or maybe starting before Easter and then finishing after Easter, depending how it works out. They belong a bit together. They both discuss the problem of finding patterns in text. There's two approaches really. One is that we spend some time on looking at the pattern closely to avoid redundant work when we find it in a new text. This is what we'll look at today. There's also the opposite idea. If your text is static and doesn't change, like it's an actual dictionary for English, but much more importantly, in bioinformatics, the human genome of a certain person doesn't change all the time. If it does, that's actually very bad news for that person. So usually it stays the same in most cells. And then it makes sense to pre-process the text, whereas the pattern might depend on the application, depending on what the doctors need to know about that person's genome. So we'll look in Unit 6 at methods how you can pre-process the text and make use of that to speed up pattern matching. But for this week and for today, we'll start with the opposite version. The pattern is fixed, and we work on the pattern first, and then we do the matching.